Hello again and welcome to another lesson. Today we are doing chemistry and I'm going to be looking at electronegativity and the periodic table. So if you understand the electronegativity and trends in the periodic table, that will cut down on your learning time, especially when it comes to learning about bonds. So let's look first at what electronegativity is. Well, in a nutshell, electronegativity is an atom's desire to hold on to electrons. It wants to, how much it wants to hog electrons. So let's look at the periodic table and the trends as we go across the row. So let's start with hydrogen. And we know that hydrogen has one orbital with an electron in the first orbital. If you're not sure what an orbital is, check out the previous video on the periodic table. But in the first row, that means that if there's two elements, we know that there are two possible spaces for electrons. So with hydrogen, we've got one electron and one space. Okay. So helium, Pauling doesn't have data. Linus Pauling was the man who worked out the electronegativities of these atoms. He doesn't have data on helium, but we know helium is going to be very high. So if I change this, and I'm just going to change this to helium. We add a second electron, and now it has a complete full orbital. So helium, it's happy, it's got its complete full orbital, and it's not going to want to give it up. So it's hogging that electron. So as we go across the table, we see the increasing electronegativity, meaning as we go across, the elements want to hold on to the electrons. I want to go to row 2 just to show how that would work. So let's look at lithium first. And there's lithium with its complete inner orbital full. And then on its outer orbital, we see there's 1 to 8 spaces for electrons, and it's only got one electron. 1, 2, 3, 4, 5, 6, 7, and then the one electron. So its electronegativity is going to be fairly low compared to others in its row. And let's look at why. Well, first of all, lithium, from the previous video, will give up its electron to become more like helium, rather than trying to gain 7 electrons. So its electronegativity is fairly low. We can also think of the electrons being attracted to the positive nucleus. Well, as we add more electrons along, the negative becomes greater. So with beryllium, let's look at beryllium. We have complete inner orbital, and then again we have 1, 2 electrons. So when we look at radius, the radius as we go across the row also decreases. And so because they're getting sucked into this positive, we can think of them as being sucked into the positive nucleus inside. And so its electronegativity wants to hold on to its electrons even more so. And we see F in red, fluorine, once we get to there, it's got 7 electrons, so complete inner orbital, and then 7 electrons in just one spare space. Okay, and so electronegativity and electron affinity are very closely related, because if I've got 7 electrons being sucked into the middle, it's really got a high electronegativity. We can see there F4 is the greatest of all of the ones we can see, except for these noble gases. But we don't worry so much about the noble gases and bonding, because they're already happy. So they don't bond with other elements. So the fluorine, high electronegativity. So as we go across the row, the electronegativity increases. So we'll be going into the bonding in the next lesson of exactly how these elements bond. But for now, we just need to know that the electronegativity increases. So it's going to want to hold on to electrons more so as we go across the table. Now, let's look at what happens when we go down the row. So down the rows. So lithium and hydrogen. So let's change this back to now a hydrogen. So it's now hydrogen again. It's now got a space. So we see that they've both got one valence electron. I'll circle that in a different color. There's that one valence electron. So that's why they're in the same row, because they've both got the same number of valence electrons. Well, look at this electron, where it is in terms of the center of the atom compared to lithium. Well, we see that it's further away. So imagine that you have a magnet. Well, the closer you hold those magnets to each other, the stronger the force you feel. And this is exactly the same. Lithium, being further away, you feel less of a strength. So it's got a lower electronegativity. So as we move down the rows, we have decreasing electronegativity. So as I move down the row, we have decreasing electronegativity as the atomic radius increases. We have further distance away, therefore less attraction to the nucleus, and so we have a lower electronegativity as we go down. And we see that in these values, 2.1, 1, 0.9, and 0.8. So finally, what I'm going to do is just finish off with an introduction to the next few videos where I will be looking at the specific bonding. And the way we work out how elements are going to bond is we look at the electronegativity between the two atoms. So let's look at if you have, say, hydrogen, which bonds with itself in hydrogen gas, H and H2. So if we look, well, hydrogen has an electronegativity of 2.1, and of course the other one does. And so when you subtract them from each other, you get 0. And this is called your change in E. And that is going to be your electronegativity of the one atom minus the electronegativity of the other. And so here we just say our change in E is 0. Let's look at if we take something like table salt, sodium chloride, we have Na, which is 0.9, and we have chlorine, which is a red one, so we know that it's high at 3.0. And we subtract that from each other, and we say that the change in electronegativity is equal to 0.9. And what we do is we usually take the absolute value, meaning I don't look at if it's a negative or positive. I just say that it's 2.1. And the way you get around that is just put the atom with the highest electronegativity first. So you'd say Cl minus Na. So I'm just going to, for the mathematicians out there, to make this strictly correct, I'm going to put the absolute value sign, which means forget the negative, I just take the number. So let's look at the change in electronegativity, because that determines the type of bond. And we're just going to summarize this and then explain it later. So if your change in electronegativity is between 0 and 0.4, we say that we have a pure covalent bond. And so that we say is nonpolar. Next video, I'll explain exactly what we mean by this. The next one would be sort of 0.4 to 1.8. Now this depends on the textbook that you're using, and often even the university you're going to. So when we were at UCT, we used 1.8. Some used 1.7, others used 2.1, but it ranges from about 1.6 to 2.1. So usually they won't give you one in between 1.6 and 2.1 because they know that there is that disparity between the universities and the institutions and what they take. But it's generally around about here, and this, we call it polar covalent. So those are covalent bonds, but they are polar. And then greater than 1.8, we say is ionic. Now, as I say, these numbers, the 1.8, there is discrepancy. You're going to see 1.6 in some places, and you're going to see up to 2.1 in others. As I say, don't bombard me with comments that it's wrong. It's just, if you go to some textbooks, you're going to see different answers. And it is one of those things where there's no consensus. But as I say, I went to UCT. I'm a proud UCT alumni, and we used 1.8, so that's what we're going with in this video. Right, so next up, we're going to be doing covalent bonding. So I'll go through the specifics of what I've been talking about here, change in electronegativity and that sort of thing. If this video helped you, please find the subscribe button somewhere down here, and like and share with your friends and all that good stuff. And I will see you in the next lesson for a bit of work on covalent bonding. Have a great day.